Remember, there are only one type of image formed by a concave lens. Just remind ourselves, put the line in, and we use this focal point, and remember it is diverging. We can put that line in, but this is my preferred line. So wherever these two lines cross is where the image goes. We describe that. It's upright. If it's upright, it is virtual. It is smaller than the original. It has got to be diminished. Let's have a quick look at the uses of concave and convex lenses. We've got the classic magnifying glass and the telescope by magnifying the detail of the image from a distance light. Let's have a look at the formulas associated with these calculations. The formula doesn't change between mirrors and lenses, and it's exactly what we've done before. These are ratios. So they are real, so are positive. And di is negative if the image is virtual. Same ratios apply to the magnification. And because it is a ratio, there are no units associated with magnification. Magnification, height, and distance are all negative if the image is virtual. Same rules apply. If you've got a number bigger than 1, we call it enlarged, the same size. Is it got to be equal to 1? Because they're ratios. And if it's less than 1, the image distance or height has got to be smaller than this, so it is obviously less than 1. It's a fraction. This is just a repeat of what we've previously seen. Exactly the same rules. We can use the SOs and the SIs, and you just remember to replace those with the distances from the focal points. Can become quite challenging, would not be a formula that I would be teaching actively, but you may see some working in some of the NCA questions, and so for the sake of completeness I'll just show you where it is. Please take your time if you want to go back over it. Let's have a look at a couple of examples from a few years ago. A 3 centimeter high object is 9 centimeters in front of a convex lens. Focal length of 5 centimeters. Calculate the distance to the image. So all we do, put our formula down. We know what the focal length is, which is 1 over 5, and we know how far it is from the convex lens, so that is going to be DO, and we can plug it into the formula, and again if we take this to the -1, that forms DI. Eye defects. We use lenses to correct eye defects. So when an image isn't falling on the retina, short-sighted is we can't see long distances clearly. So what appears to be happening is light from a distant object is not being focused on here. So what we can use is an appropriate lens that spreads that out and brings the focal point back to the retina. So we would use a concave lens before they hit the eye. Long-sighted can't see close objects clearly because the image is falling behind the retina, so we need a converging lens, so we need to bend it a bit more. This could be due to muscles, could be due to the shape of the eyeball. Either way, we need to bring this onto this point here. So we put an appropriate lens in, and it brings the light so an image is formed on the appropriate place. Drawing scale diagrams, the same applies to this as did earlier with the mirrors. Slow the video down or look at the PowerPoint would be my advice. You can do the calculations appropriately, and they are very straightforward. I hope you found the tutorial useful, just to clarify some of the main points.